First, we want to add a great appreciation to National Defense Education Program and IQ-PARC for sponsoring our work. Hello, we are the Quantum Generative art team from the summer project of Quantum Game Club at Purdue by IQ-PARC. The goal of our summer project is to create some pieces of artwork that utilize quantum concepts and ways to visualize the data of quantum circuits. As a result, we created a planetary system program with a set of planets of random size and color that rotate around the sun at random speed using the data we got from a 3-qubit quantum circuit that utilizes the quantum superposition and entanglement principles. The art piece is visualized using Blender and Photoshop. An example of an illustration of quantum superposition is the Schrodinger's cat experiment. A cat was placed in the box where a 50% of chance of poison gases may occur, which will kill the cat. So the cat can be simultaneously considered as alive and dead, as its life is linked to a random event that may or may not occur, which leads to the theory of quantum superposition. Quantum superposition principle states that a quantum particle can be in multiple states at the same time. We use linear algebra to represent the linear superposition of the quantum object. Two numbers called amplitudes describe this linear superposition. By squaring these amplitudes, we can calculate the probability of the quantum object being in one state or another. The Hadamard Gate, which is also called H-gate, is an operator which is usually used in quantum computing to bring a qubit to an equal superposition state where the probability of measuring 0 and 1 will all be 50%. If we apply the H-gate to a qubit in the 0 state, through calculation we can get a probability of measuring both 0 and 1 as 1/2. We can get the same result if we apply H-gate to a qubit in one state. Quantum entanglement explains how more than two particles can be intimately linked to each other, even if they are separated by long distances, like billions of light years of space. The particles in an entangled state cannot be described individually. A change in one of the particles will also affect the others. Entangled states can be created using an H-gate and a control NOT gate. A control NOT gate, which is also called C-NOT gate, is a conditional gate that acts on two qubits. For example, if we apply C-NOT gate to 0, state, through calculation we are still getting 0, state. However, if we apply C-NOT gate to 10 state, through calculation, we can get a 1 state. That is how we created entangled states for our qubits in our program.
In this project, our goal in creating a generative art piece with quantum computing is to express what is new and different about quantum mechanical concepts compared to the classical computers. We got this idea referencing one of the articles by Russell Hoffman. In his article, Mondrian-inspired quantum art, he explains a way to create Mondrian-style art by applying a quantum algorithm using Qiskit. In our project, we use Q-sharp and Qiskit to create a quantum art using the beauty of quantum entanglement between 3 qubits. Quantum entanglement is one of the most important concepts of quantum computing and it is very difficult to visualize. However, we try to use that concept to generate an interesting art piece. Let's start with the quantum part of our project. This is the basic quantum circuit for 3-qubit entanglement. First, we apply a Hadamard gate to the first qubit and it gives equal superposition states. Then we entangle first qubit with the second qubit using a control NOT gate. And then we entangle the second qubit with the third qubit using a control NOT gate. As a result, we get a maximally entangled quantum state which can only be either 0, or 1, 1. First, we run our quantum program on a simulator. The result gives only 0, 0, zeros and 1, 1, ones. This is the ideal situation with no errors at all. However, we run our quantum program on a real quantum computer. We also get values for states other than 0, 0, 0 and 1, 1, 1. This happens due to the imperfections of the quantum computers. In general, we consider that noise of the quantum computers must be minimized in order to get a reasonable output. However, in our project, we consider that noisiness of quantum computers doesn't necessarily have to be a bad thing, because our art piece is more visually interesting in the presence of noise. When we run our quantum program on IonQ machine as well as IBM quantum machine, we get very similar results. This histogram shows our results. Here we have higher probabilities for 0, 0, 0 and 1, 1, 1 and very low probability values for the states other than 0, 0, 0 and 1, 1, 1. To generate our artwork, we collect the dataset from the quantum machine and then we use Blender, which is an open source 3D modeling program, for the visualization part.
After receiving the histogram detailing the output of the circuit, it is brought over to a classical computer for the generation of the artwork. Here, we are utilizing Blender's built-in Python scripting feature for the generation process. First, we take the distribution of the output, creating an array containing the possibilities with their respective probabilities. This is necessary due to the limitation of the quantum machine, where it is only capable of returning a histogram combined with a long wait time in between each run. The script will scan through the array, counting every single 1, 1, 1 and 0, 0, 0 until it reaches a value that is in either of them. As previously stated, these values are created by noise that are encountered during the execution of the circuit. At which point, it will create a new object with the amount of 1, 1, 1 and 0, 0, 0 it has seen prior to this point. It will then reset the amount of non-error values it has encountered and continue through the array. We have decided to make these objects into planets, with 1, 1, 1 representing its size and 0, 0, 0 representing its rotation speed. Depending on the size of the output array, the noise will become individual planets in a solar system. With enough planets in the solar system, an art piece forms, representing the difference and imperfection of quantum computing. It is important to point out that this artwork would not be possible to create with a classical machine, as it is not affected by noise and probability. With some additional edits in Photoshop, we present our final product.